All right, so we've talked a little bit about statistics already, and now we're going to look at the probability distributions for samples. All right, now we kind of expect most sample sets or most populations, right, to have a normal distribution range. But that's not always necessarily the case if it's not a very large population, for example. Or if we just don't have enough information about the population. So we need to have a method for learning about the population's probability distribution. And so that's what we're going to talk about now. Okay? So if we talk about pennies again, the previous time we talked about pennies, we were talking about relatively small populations or samples of the population, right? So if we get a larger set from the population, here we have information for 100 different pennies, right? Okay, and we can create what's called a histogram, and this is very similar to what we were showing before. Basically, this is our actual number of the pennies that have this masses within given ranges here. So it says 2.95, 3, and 3.05, but really each one of these bars is a short, small mass interval. So from 2.91 to 3.09, right? That's our, and here 3.01 to 3.028. Okay, so that's one there. So we have these distributions. Okay. And histogram can be very, very nice, and we can see how it looks like it fits a normal distribution. And it's clear that as you increase the number of pennies, you would expect the normal distribution to be fleshed out more, and you would be able to see more clearly that we're dealing with whether or not we're dealing with the normal distribution. And you can't prove that a normal distribution will ever exist because you'll never be able to measure 100% of anything. However, the central limit theorem here basically states that given indeterminate errors, now do you remember what indeterminate errors are? Is that the random errors? Yeah, that's right, random errors. The result will approximate a normal distribution. Okay? And this holds true even if the individual sources or the intermittent errors are not normally distributed. Okay, an additional feature of this theorem is that a distribution of averages for these samples drawn from a population with any distribution will approximate closely a normal distribution. Okay, if the sizes of each sample is sufficiently large. So for example, here we have 4.46. Here we have a histogram for 10 samples of size n equals 1 drawn from a uniform distribution with a maximum value of 0 and a maximum value of 1. And B, the means for 10,000 samples for size n equals 10 drawn from the sample of from the same uniform distribution. For A, right, the mean of the 10 samples is 0.5042, and for B, the mean is 0.5006. A, the distribution closely approximates a uniform distribution in which every possible result is equally likely, so it seems here that there's no normal distribution, and that for B, the distribution closely approximates a normal distribution. So these were taken basically from the same set. And so you might think, oh, I measured these 10 values. That doesn't look like a normal distribution, but over your small range, it's hard to tell. It could be not small range, but the small number of measurements that you made, it might be hard to see that normal distribution. But again, this central limit theorem suggests that it's very hard to. It's unlikely that your distribution will not be this sort of distribution. Students don't like to hear that either, because usually there's a normal distribution around an average. If we take the test scores and say, okay, our 75% is now going to be our average, right? Instead of 50% right in the middle out of 100, right? So 75%, then we cut off this upper limit here because this would run into the 100% sooner and it wouldn't be equally distributed. That's why standardized exams generally want to have an average, a standard distribution, around the 50% of the questions. All right. Now, there's a difference between the equations for variance of population and the variance of a sample. Okay, so this is the example of a variance of a population, and this is the example of a variance of a sample. And n is our number of measurements we make, but we have another parameter which we call n minus 1, and that is what we call our degrees of freedom. Okay. The degrees of freedom is equal to the population size, n. So for our population's variance, the degrees of freedom is equal to the population size. When we measure every member of a population, we have complete information about the population. So if you have a standard deviation, n is supposed to be every member of the population, but for the square of the deviation, you use n minus 1. All right, so in the last video, we introduced this confidence interval, right? Saying that our value, the true average, will be whatever our collected average is of the n number of measurements, right? Where our average plus or minus the z value that we want to express our confidence in. So if we want to say we're more than 95%, a little more than 95%, that's 2 there, right? Divided by the square root of the number of measurements. All right? And for most analyses, we do not know the population's standard deviation, right? So we don't know about the population usually. But we can still calculate a confidence interval if we make a couple of modifications. The first modification is straightforward. We replace the population's standard deviation with our sample's standard deviation. So recall in this problem up here, right, we were always provided a standard deviation. So here they said the standard deviation from above. Here they said standard deviation of 5. Okay, so if we're not provided a standard deviation because we don't know enough information about a population, then we can use our own standard deviation. So this isn't the true, this is the sigma here, the Greek letter is the true standard deviation. S is our calculated standard deviation. Okay? That's the first modification. We can use our S, our own standard deviation, instead of the actual standard deviation. The second modification is the z value in that table. Okay? That's for our normal distribution, which is a function of sigma squared, or our standard deviation squared, not the standard deviation that we get just from our limited number of values squared. Although the sample's variance is unbiased estimate of the population's variance, the value s squared, right, not sigma squared, but s squared, will only rarely equal the actual standard deviation. So to account for this uncertainty in estimating this sigma squared, so instead of putting sigma in here, we're going to use an s, but to account for that difference, we replace the variable z with a t, where t is greater than or equal to z at all confidence intervals. All right, so you're raising it, it's greater than or equal to, so you're having to increase your confidence interval if you don't know the true standard deviation. But that's the case in most scenarios, right? Usually, you don't know anything about a population. You make 5 measurements, 4 measurements, whatever. You have an average, and you have a standard deviation, not the actual standard deviation, but the S standard, the calculated standard deviation. Does that make sense? What's the difference then? What's the difference between S and sigma?
What do you mean?
Well, we have S, and we're talking about sigma. Are you catching what the difference is?
Yeah, S is the standard deviation from, maybe 5 or 6 measurements, whereas sigma is the true standard deviation.
Very good. Now, you might have something that a lab uses as sigma, right? Nobody can ever find the actual true standard deviation because nobody's going to measure every single thing that they have, right? Every single sample that there is to measure, but that's all right. You can call it standard deviation of the population if your lab decides to call it that, okay? But this is the measured standard deviation, and this is the actual standard deviation. So if we're going to make some confidence intervals that don't have the actual standard deviation in them, then we have a fudge factor basically, which is our t's, right? Whoops. There we go. Okay, which is this t value here. There we go. Okay, so our t values are based on what we call the degrees of freedom. Now, do you remember what degrees of freedom was?
That was just n-1, right?
That's right. So if I make 4 measurements, I have 3 degrees of freedom, right? 10 measurements, how many degrees of freedom?
9 degrees of freedom.
That's right. And we have what's called a t-table, a table of confidence intervals where we don't know the actual standard deviation. And we go to the number of degrees of freedom, and then we use that t-value, and see how these t-values range. 1, if you only have 1 sample, and then, I don't know what your standard deviation is going to be, right? But you have to multiply your standard deviation by 12.706, and then divide by the square root of 1 there, so it's going to be a large error. Okay, very good. And obviously, as we approach infinity, then our value at 95%, this is all at 95%, our value for our t would be, because if we had infinity, we would basically be back to sigma again. So we'd be back to 1.96. All right, very good. So here's an example of a problem. 95% confidence interval for 2 samples of pennies in table 4.41. So here we go. We have an average, we have a standard deviation, average and a standard deviation, and now we want to use these averages and their standard deviations to express a confidence interval. Okay? So it's the average, 3.117 plus or minus. Do you remember what it was?
Well, before it was the sigma times the, the z.
That's right. So before, let's recall there, if you take your average, x bar, right, plus or minus the z times the sigma, right, and that would be our confidence interval, and the error on the standard deviation would be identified when we divide that by the square root of n, right? So what's different here?
Well, we don't have the sigma.
We don't have the sigma, but we have what?
We have S, which is the calculated standard deviation.
Very good. So instead of doing this, we're going to take S, our average, which we calculate, S, and what?
Well, instead of Z, we're going to use the t-value.
T-value.
And then the divided by the square root of n again.
Divided by square root of n. And, all right, so I wrote these down. Did I write these down? There's 3.17 plus or minus. Got to finish that one. And here's 3.081 plus or minus. I'm going to write down the standard. This is the average. I'm going to write down the standard deviation below it. 0.051, 0.037. This is our standard deviation. All right. Okay, so what do we do now?
It's way down there. Okay. Nope, not yet. There's our t-table. Okay, so now for the first one, 3.117, that was for 7 measurements, right?
Yeah, that was for 7 measurements. Should we go back up?
Yeah, I guess so. Seven measurements, and that one was for 5.
Okay, good. So what's that mean?
Well, you go to degrees of freedom is 7.
No, remember degrees of freedom is n minus 1.
Oh yeah, 6. So 2.447 is our t-value.
Okay, so our t-value here, this is the plus or minus for this thing here, that's not being a minus t. Our t-value is, what do we say?
2.447.
So we need a 2.447 instead of the 1.960 if we are using our own standard deviation. And our own standard deviation is 0.051, 0.051. And then I divide that. I do get to divide it by what?
Plus or minus 7.
That's right. Sorry, not plus or minus, but n equals 7. So divided by 7 there. All right. So 2.447 times 0.051 divided by the square root of 7. And what is that going to tell us?
That's 95% confident that what? That the average is within that range, 3.117 plus or minus. What is that value?
Here, let me get out my calculator here and let's give it a shot. Okay. 2.447 times 0.051 divided by the square root of 7. 0.047. So 3.117 plus or minus 0.047. All right, so how are we going to report this value?
It's just going to be 3.12 plus or minus 0.05.
Very good. 3.12 plus or minus 0.05. Okay, very good. And this one over here is 3.081 plus or minus 0.046, and that needs to be, again, 3.08 plus or minus 0.05, right? It really isn't correct to report more area or values of uncertainty and to include this value then if you're uncertain at this second value, right? Okay, good. Want to do another one?
We could look at it.
All right, what's the 95% confidence interval for the sample of 100 pennies?
Oh, okay. Well, it's nice they give us the mean and the standard deviation.
Yeah, that's nice. So it should be pretty straightforward, right?
Yeah, so you get your mean.
3.095. Then what?
Plus or minus.
Plus or minus.
You got to get a t-value for 100. T-value for 100.
Very good. We had 100 pennies sampled. So t-value for 100, 1.984.
Oh, that's pretty low.
Yeah, that's pretty low, huh? So 1.984. What do I do with that?
Multiply that by the by our standard deviation, 0.0346.
So 1.984 times our 0.0346. And then what?
Oh yeah, divided by the square root of wait a second. Did I do that t-value right?
I think you're right. I think we made a mistake there, didn't we? It's not quite 1.984.
No, it's not. It's supposed to be n minus 1.
That's right, for 99. But we don't have a table here, do we? Or we don't have that on our table.
No, we don't.
So there is ways in Excel to find the t-value if you don't have a table like this, okay? So we'll talk about that in a bit. For now, we'll just use this, and we'll look and see exactly how they did it as well. But we divide this by what?
Square Square root of 100 or 10.
Very good. Square root of 100, that's the number of measurements we have. So we'll look at the answer here instead of doing it on the calculator ourselves. Let's see. With 100 pennies, we can approximate its value by using t 0.0560 and t 0.05 and by assuming a linear change in its value. Okay, so they approximated between 60 and 100. That's fine. But I'm going to show, we're going to go through Excel and see how we can always have access to that t-table. Not that it's hard to have access this way, right? What is the t-value for 100 samples? Okay, so values of distribution, here we go. So we can get to 100, 90, they didn't even give us 99. Maybe we have to ask for 99 samples. What is the t-value for 99 samples? Let's see if we can get 99 samples there. I don't see that. But this t-table does do something else that we haven't discussed yet. This t-table here gives us t-values if we want to express our confidence in something other than 95%. So like if we wanted to say I'm 50% confident, or I'm 99.9% or 99.5%, we can use, there are different values, t-values that we can use for that table. Okay, so let's get into how to do this in Excel. Okay, so here are the steps to find the confidence interval in using Excel. Okay, the first thing we need to do is we need to prep our Excel. And we're going to do that by going over here to File and then clicking on Options. And then down here, we're going to click on Add-ins. We're going to click on Add-ins here. And then after we click on Add-ins, we have to go down here and where it says Excel Add-ins, we're going to click on Go. Okay. And then once we do that, we need to make sure that we have the Analysis Pack and the Solver add-ins included here. And then we say OK. All right. Analysis Pack and the Solver. And then after we do that, we should be able to see those up here in our data. So if we click on data, we should be able to see our data analysis there. Okay. So now if I click on our data analysis window here, our data analysis sign here, then that's going to bring up this option of different statistical analysis. And the one that we want to do is this descriptive statistics. All right. And then I say OK. And this is going to have my confidence interval as one of the outputs. Okay. So here I want to identify the input range. So I am going to I have collected all of these 1 through 100 different penny masses from up above, right? So I click those, select those, and then I select OK. And it asks me if this is grouped by rows or columns, and it's grouped by a column, so I just leave that there. If I had a label up there, I'd want to push that, but I don't have a label, so I'm OK. And now the output range, I can choose where I put the output range. Or I could just do a new worksheet, and that's probably just as good to do a new worksheet. So I'll leave it at that. We would want to make sure that we have the confidence level indicated here. So here's where you would say what confidence level you want to use, and we are going to be using 95%, or for most scenarios in your existence, you'll be using 95%. Okay, and that should be it. So then we can click on OK. Oh, sorry, we want to get summary statistics. Click there as well. And we click on OK. And then after that, I can, I like to just copy this and bring it back to the same sheet here. Put it up right here. I'm going to paste, and we're just going to paste special, paste the values. There we go. So what do I have here? I get back the average. I get back my standard error, right? And then I get back my confidence interval down here. I have a variety of other things that it gives me back. But this is my average, and this is my confidence interval. So 3.09, this is at the third decimal point here, so 3.094 plus or minus 0.006. And I could say that I'm 95% confident that all of so basically 95% of the measurements that are made, that's what 95% confidence means, will be within that window of the average. All right. So let me copy this down here just to make sure we know what's going on here. Pasting it there. I'm going to copy this here and paste it here. Right. And then in here I'm going to put my sign, right, my symbol.
Your plus or minus symbol?
Yeah. There we go. Okay. One too many times. There we go. So that is my confidence interval then. Okay. So now in this scenario, it has a t-table, and it looked up t equals for n, or for 99, 99 degrees of freedom, right? Now, do you remember how that 99 degrees of freedom relates to our experiment?
Well, you made 100 measurements and your degrees of freedom is 99.
Very good. All right, so if I didn't have the table for the 99, I can use Excel's table. Let's see, where should I cut this off at?
The third decimal point.
That's right, good. So the number, only 3 decimal places. This one also, number, 3 decimal places. Okay, very good. What happened there? Oh yeah, that's right. Okay, excellent job. So that's using Excel to find our confidence intervals, which I think is a good idea to learn how to use, because if you do it once, you'll forget in the future, but you'll always be able to go to YouTube and ask somebody how to do it, and they'll be able to show you. If you don't know what a confidence interval is, then you won't know what to ask. Okay, good.